The world of AI often feels like, well, a relentless race for bigger, more powerful models. It's almost this unspoken rule. More parameters, more intelligence, more resources needed. But what if a smaller model, one that's far more accessible, could not just keep up, but actually outperform its much larger, resource-intensive rivals?
Welcome to AI Paper Podcast. Today we're doing a deep dive into a paper that seems to completely redefine parameter efficiency in advanced reasoning systems.
Yeah, we're talking about K2Think, a parameter-efficient reasoning system. This comes from the Institute of Foundation Models at the Mohammed bin Zayed University of Artificial Intelligence. And it's a really innovative approach, definitely challenges a lot of our current assumptions.
Okay, so for our listeners who might need the quick takeaway, here's your, let's say, 1-minute summary. Get this. K2Think is a 32 billion parameter model, and it's achieving frontier performance, often surpassing or matching models like 4 times its size. We're talking GPT-OSS 120B and DeepSeek v3.1. Exactly, and it does this through a brilliantly synergistic approach. This involves advanced post-training techniques, some clever test-time computation strategies, and even inference-optimized hardware. And really importantly, it's all built on publicly available open-source datasets.
So this combination makes K2Think the new state-of-the-art for open-source mathematical reasoning. That's huge.
Right.
While it also maintains incredibly strong performance in code and science, too. It's proving that maybe top-tier reasoning capabilities can be far more accessible, more affordable than many of us thought possible.
Right. So our mission for this deep dive is to really unpack this ingenious recipe. We want to understand precisely how each component contributes to its impressive capabilities and, what this all means for the democratization of advanced AI. Okay, let's unpack this then. The core idea here is radical parameter efficiency. What makes K2Think stand out so dramatically, especially given its relatively modest size compared to, the giants out there? Well, what's fascinating, I think, is that K2Think hits this frontier performance with just 32 billion parameters. This directly challenges that common notion, that you need orders of magnitude more parameters to compete with the leading reasoning models. It's really a significant shift in perspective for the field.
So hold on, we're talking about a model that can rival systems like GPT-OSS 120B and DeepSeek v3.1, but it's 4 times smaller, maybe even more. That's a pretty bold claim, isn't it? Especially for an open source model.
It is indeed a very bold claim. And it's not just comparable, you see. In many cases, it's actually surpassing them. Particularly, and this is key, in complex mathematical reasoning tasks. It consistently shows superior parameter efficiency. That's against both open source and proprietary models.
Okay, so why did the researchers specifically choose a 32 billion parameter model? I mean, based on Qwen 2.532b. Seems like a very deliberate choice, right? To make such a big statement with a, relatively speaking, smaller base.
Yeah, that 32B scale offers several strategic advantages. It allows for fast iteration during development, which is super important for research. It provides strong base capabilities to build upon, so you're not starting from scratch. And importantly, it's a size that suits both advanced research and more consumer-grade computation frameworks. So wider usability. Oh, and critically, Qwen 2.532b wasn't originally tuned for reasoning, so that made it an ideal sort of blank slate base to really validate the effectiveness of K2Think's full enhancement recipe.
Right. Okay, here's where it gets really interesting, I think, especially for anyone actually building AI systems. K2Think isn't just one single breakthrough, is it? It's described as an integrative recipe built on 6 key technical pillars. Can you walk us through them? Because it feels like this combination, this synergy, that's the real magic here.
Absolutely. That synergy is crucial. These pillars are combined across both post-training and test time stages. So on the post-training side, we have long chain of thought supervised fine-tuning, or SFT, and then reinforcement learning with verifiable rewards, they call it RLVR. Then for test time computation, there's agentic planning prior to reasoning, which is neat, test time scaling using best of n sampling, speculative decoding, and finally, inference optimized hardware. It's truly an end-to-end system designed for efficiency.
Okay. Pillar 1, Supervised Fine-Tuning, SFT, specifically with long chain of thought. How did they apply this? How did it build K2Think's initial reasoning chops?
So this initial stage, it involved fine-tuning that Qwen 2.532b base model. They used curated long chain of thought, or CUTO, traces. These came from the AM Thinking V1 distilled dataset. And the goal was essentially to give the model explicit guidance for generating structured step-by-step reasoning processes before it spits out an answer, basically teaching it to show its work,
And the results, what were the immediate results from this SFT phase? Did they see big gains right away?
Yes, actually quite rapid and significant gains. They saw a dramatic performance improvement, particularly on those challenging math benchmarks like AIM 2024 and AIM 2025. This happened within the first third of training, around half an epoch. Performance then plateaued, but it reached pretty impressive pass at 1 scores. Pass at 1 means getting it right on the first try, like 79.3% for AIM 2024.
Wow, okay, so big gains early on. Did it also improve the model's ability to maybe explore multiple potential solutions? Because that's often crucial for complex reasoning, right?
It did, yeah. Figure 3 in the paper highlights this with pass at case scores. The SFT model dramatically outperformed the base model across various sampling budgets, like how many attempts it gets. It showed a much stronger ability to explore and find solutions, eventually saturating near 93.3% accuracy by the time chaos was around 128. So this strong performance, while not perfect, definitely indicated an opportunity for more refinement during the next stage, the RL stage. It set a really solid foundation.
Okay, so after establishing that strong SFT base, they moved to reinforcement learning with Verifiable Rewards, RLVR. What exactly does Verifiable Rewards mean here? And how is it different from other common RL methods, like, say, RLHF?
Right, RLVR. It directly optimizes for the correctness of the model's generations. And that's a key distinction because it significantly reduces the complexity and, frankly, the cost often associated with preference-based alignment methods, things like reinforcement learning from human feedback or RLHF. RLVR is focused purely on objectively verifiable outcomes like, did it solve the math problem correctly, rather than subjective human preferences.
Makes sense. Which data sets did they use for this phase then, and what domains did it cover? Did they try to ensure broad applicability beyond just math?
Good question. They used the Guru dataset, which is actually quite comprehensive. It has nearly 92,000 verifiable prompts across a really wide range of domains, including math, obviously, but also code, science, logic, simulation, even tabular tasks. So yeah, definitely not just specializing in one area. They were aiming for general reasoning improvements.
Okay, now what were the key learnings from this RLVR phase? I heard there were some perhaps surprising, maybe even counterintuitive observations, things that could influence how we approach training in the future.
Oh, absolutely. This raises a really important question for anyone designing these systems. How does the strength of that initial SFT checkpoint influence the later RL stage?
Yeah.
What they found was, well, while starting from a strong SFT checkpoint did lead to better overall performance in the end, it paradoxically limited the absolute gains they got from the RL phase itself. So RL training starting just from the base model showed nearly 40% improvement. Huge jump. But RL starting from the already strong K2-Think SFT checkpoint, that only yielded about 5% improvement.
Huh. So if I'm hearing you right, there's this fascinating trade-off, like too much initial fine-tuning, being too good at the start, might actually stunt the model's long-term adaptability or potential gains from reinforcement learning.
That's a really counterintuitive lesson for anyone designing training pipelines, isn't it? Suggesting you need to leave room for exploration. Exactly. It seems heavily SFT models might become sort of constrained, less able to explore alternative reasoning strategies during RL. And another unexpected finding related to training setup. Multi-stage RL training. They tried reducing the context length initially, say, from 32K tokens down to 16K before expanding it again later. But that actually degraded performance. It failed to even match the baseline SFT model. So it suggests that messing with the context length, cutting it below what it saw during SFT, can really disrupt the model's established reasoning patterns. It's not some universally good trick.
Interesting. Okay, so moving beyond the training phases, K2Think also uses clever techniques at inference time, right?
Yeah.
When you actually use the model. Tell us about this plan before you think. That sounds intriguing, like a meta-level approach to problem solving.
Yeah, plan before you think. It's essentially an agentic planning step. Think of it as a smart pre-processing phase before the main reasoning happens. An instruction-tuned language model acts as an agent. It first extracts the key concepts from the user's query, and then it creates a high-level plan for solving it. This plan is then just appended to the original query, and the whole thing is fed to the K2Think model as a structured prompt. The idea is conceptually rooted in cognitive science, seeing planning as this meta-thinking process that guides the actual reasoning.
Okay, that makes sense. And then best of n sampling comes in after that, right? To kind of refine the outputs and ensure quality.
Precisely. Best of n, or BON, sometimes called repeated sampling. It's where the K2Think model generates n independent outputs for the same prompt. In their case, they found n3 was optimal for K2Think. Then, an independent LLM acts as a sort of reward model or verifier. It selects the best response, usually through pairwise comparison. It's basically about getting multiple shots on goal and then picking the best one. Standard practice, but effective.
Did they try other test time methods? I mean, there are lots of tricks people use. What made these two, planning and bond, so effective while maybe others weren't? Especially considering how much engineering goes into these things.
Oh yeah, they explored a lot of different approaches, things like temperature tuning, extensive prompt engineering. They tried over 30 different system prompts. And more sophisticated scaling methods too, like re-2, self-consistency, co-T with reflection, even mixture of agents, or MoA. But most of these actually yielded negligible gains, which is itself an interesting finding. MoA did deliver marginally better performance, but Best of N was ultimately selected for the final K2-Think system. Why? Because it had a significantly lower computational cost. And that's a huge factor in practical deployment, right? Cost matters.
Absolutely. So what's the impact when these two methods, plan before you think and Best of N, are combined? Do they work better together? Is there synergy there too?
Yes, absolutely. It's that synergy again. The component analysis in Table 2 clearly shows this. While Best of N sampling provides the bulk of the improvement over just the post-train checkpoint, combining it with the plan before you think prompt restructuring offers significant additive gains. We're talking 4 to 6 percentage points of improvement across all the math benchmarks just from adding the planning step. It really helps.
And I heard something about plan before you think having a surprising side effect. Beyond just getting better answers, maybe something related to efficiency.
It does. Yeah, this was pretty cool. Table 3 demonstrates that not only does planning improve the response quality, but it also reduces token expenditure in the final response by up to nearly 12% on some benchmarks. For instance, OmniMath Hard saw an 11.73% reduction in tokens used. So this means K2Think provides more concise yet higher quality answers. It's kind of a win-win for both performance and efficiency. More value per token.
Okay, all these techniques sound incredibly powerful. But, long reasoning chains, like the ones needed for complex math proofs, can often mean slow inference times. How did they tackle that? How did they make K2Think practically usable, not just theoretically impressive for researchers sitting in a lab?
Right, that's crucial. This is where the final two pillars come in: speculative decoding and the Cerebras Wafer-Scale engine, or WSE. Speculative decoding is a clever technique. It allows the model to sort of guess ahead several tokens at once and then verify those guesses efficiently. It speeds up generation significantly. And the WSE itself, well, it's leveraged as the world's largest processor. By keeping all the model weights in its massive on-chip memory, it basically eliminates the memory bandwidth bottleneck. That bottleneck is what often severely slows down these autoregressive models when they run on traditional GPUs.
Wow, specialized hardware. That sounds like a potential game changer. How much of a real-world difference does this actually make for users interacting with the model? Is it noticeable?
Oh, it's dramatic, a huge difference. The WSE delivers approximately 2,000 tokens per second. Compare that to the nominal 200 tokens per second observed on typical deployment environments like NVIDIA H100 or H200 GPUs. So that's a 10 times improvement. To put it in perspective, a complex 32,000 token response, which isn't uncommon for challenging mathematical proofs, that can be completed in just 16 seconds on the WSE, compared to almost 3 minutes on an H100.
16 seconds versus 3 minutes. Okay, that's a fundamental shift. It totally transforms the user experience, doesn't it? From a kind of batch processing mindset where you wait ages to truly interactive reasoning, which is especially crucial for those multi-step reasoning pipelines we've been discussing. It makes complex tasks actually feasible in something close to real time. All right, so after all this innovative development, the 6 pillars, the hardware, how did K2Think actually stack up? How did it perform against other frontier models in rigorous, comprehensive evaluations across different domains? Did it truly punch above its weight?
It absolutely did. Yeah, the evaluation results are pretty compelling. They compared K2Think against both open weight and proprietary models, and they used challenging benchmarks in math, code, and science to give a really holistic view of its capabilities.
Okay, so specifically in math, which was its primary focus, where did it land against the leading models there?
So K2Think, remember, it's a 32 billion parameter model. In math, it delivered truly impressive results. It achieved top-tier scores across advanced benchmarks like AIM and OmniMath Hard, but what's really remarkable is that it didn't just outperform similarly sized models by a large margin. It actually surpassed much larger open-source models, including DeepSeek v3.1, which is 671 billion parameters, and GPT-OSS 120b. It even got close to the performance of some powerful proprietary systems on the hardest questions. So yeah, it clearly showcased its ability to solve the most challenging math problems despite its size.
That's seriously impressive for math. What about its performance in code and science? Did it show versatility beyond just math?
It did.
Yeah.
It demonstrated robust and competitive capabilities across those domains as well. On LiveCodeBench, for coding, it significantly outperformed its similarly sized peers. It even beat the much larger Qwen3 235B model. For SciCode, another coding benchmark, it was a very close second to that same huge Qwen3 model. And scientific reasoning on the GPQA Diamond benchmark, K2Think scored higher than most open source models in its class. So this pattern of strong performance across diverse domains really underscores that punching above its weight philosophy. It's not just a one-trick pony for math.
Okay, releasing such a powerful model openly, especially one good at reasoning, demands a strong commitment to safety, right?
Yeah.
Responsible AI deployment. How did the team evaluate K2Think safety profile against potential misuse? What did they look at?
Yeah, very important point. They systematically red-teamed K2Think using established public safety benchmarks. They consolidated the results into 4 key aspects that are relevant for real-world deployment. It gives a pretty clear operational safety profile.
And what were the results for things like high-risk content refusal and conversational robustness? Did it hold up well in those critical areas?
It performed quite well there. K2Think showed an extensive ability to avoid generating high-risk content. It got near-perfect scores on a majority of the benchmarks in that category. It also exhibited notable robustness to sustained adversarial dialogues. So it consistently maintained refusal behavior even when people tried to trick it over multiple turns. So strong performance there in those key safety areas.
Okay, that's good to hear. And what about on cybersecurity, data protection, and jailbreak resistance? Were there any areas for improvement there? Because these are often really tough challenges for any large language model.
Right, those are definitely harder areas. And yes, here, there's indeed more room for improvement identified. While it demonstrated good robustness against leaking personal information, which is great, it did show some susceptibility to prompt extraction, getting it to reveal its system prompt, and also potentially aiding in cyber attacks, scoring lower on those benchmarks. For jailbreak resistance, it performed strongly when attacks were direct and obvious, but it showed apparent weaknesses to more indirect, sneaky methods like do anything now prompts or latent jailbreak techniques.
Okay, so summing up the safety evaluation then, what's the big picture takeaway for K2Think's overall safety profile right now?
Well, the overall safety evaluation indicates a solid baseline of safety, especially in refusing harmful content and maintaining consistent conversational behavior, which are fundamental. However, it also clearly highlights opportunities areas where they need to strengthen defenses, specifically around cybersecurity, jailbreak robustness, and maybe fine-tuning its refusal calibration. It's a strong start for an open model, definitely. But they acknowledge and are actively working on improving it further, which is exactly what you want to see for responsible open deployment.
Okay, so stepping back, what does this all mean for us, for the field? K2Think seems truly a remarkable achievement. It really demonstrates that you don't always need the largest models to achieve frontier performance. It's a powerful counter-narrative, isn't it, to that kind of bigger is always better mindset, especially when resources and accessibility are concerned.
Indeed. I think it's a powerful validation of the core idea that a synergistic combination, sophisticated post-training, strategic test time computation, and optimized hardware can empower smaller, more accessible models to really punch above their weight in complex reasoning tasks. It truly redefines what's possible with thoughtful engineering and optimization rather than just brute force scaling.
And the fact that the team at MBZU AI has made K2Think freely available is huge. The code, the model weights, and even a public web portal at K2Think.ai, you can actually try it out yourself. That really embodies an ethos of open science, doesn't it? Democratizing access to cutting-edge AI, which is fantastic.
Absolutely. This commitment to open deployment is crucial. It's so important. It means K2Think isn't just, a paper or some static artifact locked away. It's a living system that the community can actually stress test, build upon, iterate on, and that helps push the boundaries of what's possible in AI research and application for everyone. It fosters collective learning and innovation in a way closed models just can't.
Yeah. This deep dive into K2Think really makes you wonder. With such clever engineering, could the future of AI progress be less about just relentless brute force scaling and more about discovering these innovative, parameter-efficient recipes, finding smarter ways to get more out of less? It's certainly something for us all to mull over as the field continues to evolve at this breakneck speed. Well, thanks for joining us for this deep dive on AI paper podcasts. We hope you're leaving as informed and maybe as curious as we are.